Some physical quantities are represented by a single number or a value, a size only. So things like temperature, let's say 20 degrees Celsius, density, 1 kilogram per cubic meter, speed, 5 meters per second, or distance, 5 meters. But there are some physical quantities where a single number is not enough. You need a size and a direction. For example, you could talk about velocity. It's not enough to say 5 meters per second. You also have to specify a direction. Let's say 45 degrees north of east. There's something called displacement. When you displace an object, that means you're moving it from one location to another. And so what you need to know is the direction in which you moved it, something like horizontally. This difference in requirements led mathematicians to talk about a new type of object called a vector. This word has Latin origins, and the word vector in Latin means to carry. And that implies that we are somehow interested in moving things. Now, it's very natural to represent vectors as arrows. So, for example, you could talk about an airplane that's flying through the sky. Let's say it's moving this way. It has some sort of velocity. Now, this arrow represents the vector. The larger the arrow, the larger the size, and the direction simply tells you which way you're going. This is the notation that we're going to adopt. We're going to put a letter to represent the vector, and we will put an arrow hat on top of it. Now, when you see vectors in print, they will often put them in bold font. The other thing that we are going to do is make this notion abstract. So we're going to say that a vector starts at some point A and then terminates or ends at some point B. So a vector is a directed line segment. A is what we'll call the initial point, and B is what we'll call the terminal or ending point. With those basics in mind, vectors are equal if they have the same size and direction. So if you take a look at it, as long as the angle that it makes relative to something and then the length of the vector are the same, then we'll say that the vectors are all equal. So for example, I could call this one W and I could call this one Y. In all of these cases, it doesn't matter if the vector is in a different location in space, it's the same vector. So it does not depend on location. Now, a natural consequence of that is that there are infinitely many ways to represent a vector with an arrow. Now, there is a very special vector, and this is going to be denoted by a 0 with a hat, and we're going to call this the 0 vector. Now, the 0 vector has essentially no size and any direction we want. And the direction is in some way irrelevant because of the 0 size of this vector. The size or the length of a vector, we are going to give a special notation to. We're going to put the vector in these absolute value bars. And this is just a number. Note that the length of the 0 vector we are going to take to be the number 0. And if you could visualize any other vector, essentially it's like saying take a ruler and measure how long this is, and then the length of that segment would be V bar. We will talk about how to calculate the length of a vector a little later on. Another important thing that we need to do is to be able to work with vectors. Now, working with vectors essentially boils down to 2 vector operations. And so the first is what's called scaling a vector. If you have a vector, it's possible that you would like to make this vector longer or shorter. You could make the vector twice as long as it was before, and in that case we will write it as simply a 2v, or you could make the vector a half of what its original length was. In that case, we'll write it as a 1/2 v. We will write down any scaled version of our vector as some constant times v. This constant we're going to give a special name to. We're going to call it a scalar because its job is to scale the vector. It's like a dial on a machine. As you turn this dial, it makes the vector longer or shorter. So this operation right here is called scalar multiplication. Now note, if we have this number in the front being a positive number, that means our vector CV is in the same direction as our vector V. We will say that they are parallel vectors. But it's very much possible to have a negative number in the front. So for example, if I put a -1 in front of the V, we're just going to simplify this as -V. How should we interpret that? Well, what this is going to be taken to be is that we're just going to reverse the direction. Same length, but just opposite direction. Sometimes we call this anti-parallel. Now, the length of a scalar multiple, if you have the length of a scalar multiple, let's say c times some v, it's just going to be the length of the original vector times that scaling factor. But we are going to be a little bit careful, and we're going to put an absolute value here. Because, for example, if I say what's the length of 2v, we're just going to take it to be twice the length of the vector v. But if I say what's the length of -3v, we don't want the length to be a negative number. We're always going to take the length to be a positive number. And that means we will take the scaling factor out and then take its absolute value and simply multiply that by the length of the original vector. The length we are always taking to be a number greater than or equal to 0. The length of the 0 vector is a value of 0. Now, the other operation that we need to talk about is addition. If I have an airplane, if it's flying that way, there's the velocity of the airplane. And if there's some wind blowing, now the plane is going to get pushed by the wind. So somehow we need to know which way this plane will end up going. And what that means is we need a reasonable way to understand how to add these two vectors. And so we will talk about just this notion of pushing. So if I had my first vector here, u, I would start at this initial point. It would take me to this terminal point. And let's say there's a second vector now, w, that takes me and pushes me from there. So the net result is that I started here and I end there. So this resultant vector will be u plus w. And we say that we are going to add vectors tip to tail. And what that means is we will put the tail of the second vector right beside the tip of the first vector, and then we will connect the dots from the initial point all the way to the terminal point of that second one. Sometimes this is called the triangle rule, because you can see that it makes a triangle. Another way to interpret it, because remember, there are infinitely many vectors that we can use to represent a single vector. So we could, for example, say take the same vector u. We could take this w and have them both start at the same location. And what we could then do is make a parallelogram where the length of u and the length of w represent the sides of the parallelogram, and then this resultant vector would end up taking us to the same place. So another way to calculate is by something called the parallelogram rule. We could then talk about subtraction. Now, when you talk about subtracting two vectors, let's say u minus w, what we're going to do is interpret that minus sign as addition of a negative w, which is the same as saying reverse the direction of w. So if we had our vector u here to begin with, and if our vector w went like this, negative w would point in the opposite direction. So what we would do is we'd use either the parallelogram rule or the triangle rule, and we would now work with u and negative w. And then this result right here would be how we perform vector subtraction. It's essentially vector addition with w that points in the opposite direction.